Okay. Yeah, hello everyone. We got a lot of people on here. This is good to see. Picked up a few more just in the last minute, so glad we stuck around. Thanks for being patient. Lots to share today. We're going to be covering quite a bit. So I do this, well, yeah, first of all, my name is Chris Fregley, founder of PipelineAI. Essentially, our mission is to bring a lot of the best practices from, behind Uber, from behind Netflix, from, behind Google, and best practices and bring them to the masses. So what I mean by that is, pretty much end-to-end pipelines. So starting as very basic as Jupyter Notebook and getting the ability to connect to some data sources and get that data trained and saved as a model that can then be served in production. We're very production focused. We spend a lot of time on the production side of things, meaning getting these models out into application developers' hands. So when we say production, we mean REST endpoints or Kafka Stream, right, like Kafka Stream consumers, things like that. So depending on who you talk to, the term production means something different. If you talk to a data scientist, typically production to them means moving their model off of their laptop and onto, and pointing to, like a larger S3 bucket. That's not the type of production that we're really focused on, which is more, creating a data product like a machine learning model, AI model, pushing that behind a REST endpoint. That's kind of the last mile of application, sort of AI-focused app engineering and the ability to give app developers access to these trained models. So, really a lot of our training is with production and performance in mind. So you'll see us discuss quite a bit things along optimizations. Okay, so a couple things to point out. Let me just get my browsers set up here. Boom. Just hold for one more second. I want to show you guys everything that's possible. So one big thing that happened actually a couple months ago, so right before Christmas, right before Thanksgiving, actually, the holidays, there was this project called, let me share my screen here. There's a project out of Amazon called SageMaker, and it's the AWS SageMaker. It's essentially the last mile for your machine learning. They also have in it a nice notebook as well too. So I'm going to show some examples there. And I'm going to show you one really interesting piece of that product. When it was first launched, I had a lot of friends ping me and say, hey, isn't that what Pipeline's doing? And, to some extent, yes, we are tackling the infrastructure problem with machine learning. And we want people to spend more time on the modeling and less time on the infrastructure. So let me share my screen here. A little bit busy. But let me make it a little bit simpler here. But one good thing is that the Amazon SageMaker actually encourages people like us that have optimized runtimes for our model serving to still be able to build and upload into SageMaker our own runtimes in the form of like Docker images, custom Docker images. So that's kind of our niche market there. Our real value add is, providing very easy ways to get your Scikit-Learn models, your R models, your Python, just plain Python code into burned in Docker image that can then be uploaded into SageMaker and can very quickly start taking predictions. And so I'm going to show you guys the flow, how we're going to do that here. Okay, I should be sharing my screen now. Hopefully you guys can see that. If not, ping me. Also, if you have questions, you can use the chat. There's a little chat thing here. I will keep an eye on that. I'm not going to stop for every question just because we have too much to cover, but at the end, I will pipe in here and answer all of them. Also, I can stick around for a little bit afterwards, so if there are things that you would like to know, I could stick around and answer them. Make sure when you post that you actually post to the entire group and not just to me directly. That way, right, like other people can possibly answer the question, or will save me from having to re-type the question. All right. So I got the dashboards up here. I do want to point out, I've spent a lot of time this past month getting the documentation a little bit up to speed here. So made some changes here on this side of things. You know, this is kind of the front page off PipelineAI. Still, you know, pretty much the same, but up here you'll find a community link. And you can also, we're starting to see quite a bit of people sign up for the Slack channel, which is really cool. So just click on this link, and there's a public Slack channel support. I found this actually much more useful than kind of email ticket systems. People are just more likely to engage when they you know, think that there are other people on the Slack channel. They can see other people on the Slack channel. It's more of an interactive thing. So we've had some people answer questions, other people's questions, which is really nice. Also, just to remind you guys, you know, this is an open source project. We're approaching 2,300 stars, pretty active project. You can click there to get to the GitHub. You can click join Slack channel for the Slack. You can try out. So we have this community edition that maybe not all of you know. As long as you have GitHub or Google or Facebook or anything, you can log in, or Twitter. That's your way of logging in. Now, this is a shared community edition. This is actually this is an implementation of the pipeline full like enterprise, but it's single user, you know, it's a shared environment. So don't upload anything sensitive in there. And we can delete anything at like any given point in time. So, you know, here's some people trying out some sample data, things like that. Looks like the Fast AI folks were in here trying things out. Bunch of sample notebooks. So we got SageMaker notebooks and GPU. We run a monthly workshop as well too, which is, you know, these are all the like notebooks here. This is a GPU instance. So if you don't believe me, we can go here and run our favorite NVIDIA SMI, and there it is. Let's see, 28 degrees Celsius. It's running pretty cool right now, so it's not seeing too much action. But and we also have XLA turned on now. I just upgraded this to be a very recent version of TensorFlow. I believe it's going to report 1.41 here, but it's actually and I just upgraded again last night, and I'm going to push it today after the call. It's right at 150 RC1, which just dropped a couple days ago. So yeah, so try things out there. A couple people, looks like maybe they're hitting it right now. So this is this monthly developer online meeting. Here's our global meetup. We posted a couple more videos over the past month, and a bunch of more presentations since December, right before the holidays and stuff. So all the materials should be there for you. I think pretty much everything here is pretty much the same. Just maybe tweak this a little bit. There's more info on the workshop if you're interested. And also been working pretty closely. We're actually have a couple more people to add to the integrations tab here. So, you know, these are people that use our REST API or CLI from within their product to, once a model has been trained, they can then get it out behind either Kubernetes, you know, Docker Swarm, or this new SageMaker service. So I'm heading up to Seattle next week. I'm going to be meeting with some Microsoft folks and Amazon folks, and also one other product, Algorithmia. That's like pretty interesting. So, and I met with the Domino folks this past week. Yeah, so last week to get them to be integrating with us like pretty cleanly. Also, there's one other company, datascience.com. And we're starting up a POC with them in the next week or two to extend their product to deploy models in a Netflix, right, like Uber-like fashion. Okay, so let me kind of kill these here. Also want to point out, so if we go to community and go to the GitHub, the main project here is Pipeline, which is where you'll see all the, so we cleaned up some of this documentation. One thing to point out, we've added these quick starts. Also, we have a big link here for Slack because everyone seems to like it. One big release that happened over the last week was Docker now supports Kubernetes, and this is Docker for Mac. I believe Docker for Windows will soon be supporting it, but if you haven't upgraded it, the one caveat is that it's on the experimental edge version, not the stable version. So this is a bit bleeding edge. I always run the edge on my local machine, and it has a bit of quirks here, but it's still super stable, relative to other edge things that I've seen. So if you notice now there's this Kubernetes thing over here, you just click that to enable it. And what else? Advanced. One thing I'm trying to encourage is 4 CPUs, 8 gig memory minimum. If your machine only has that, then you might be running pretty warm. My MacBook, pretty much the fan's running all the time now because of this Kubernetes stuff. So what's cool is that you don't have to do little hacks and things with like Minikube, and I still do use Minikube for some stuff that this version of Kubernetes doesn't support very easily, or it's a bit hokey, but for the most part, you can pretty much do everything. So today we're actually going to go through and do, we're going to go through the steps to deploy to SageMaker and also to our local laptop using just Docker and then using Docker plus Kubernetes. So basically these first 3 links here, actually all 4 links. And I'm going to do this in my usual non-linear fashion, so that might drive some of you crazy. But I'm here to tell a story, so if you just sit back and listen, and hopefully I can express the story. So we'll be covering GPUs. We're going to deploy on SageMaker both a CPU version of our TensorFlow MNIST model and a GPU version. We're going to deploy them in behind one endpoint and allocate 50% traffic to go to one, 50% traffic to go to the other. Then we're going to load test and see if GPUs really are faster than CPUs. So that'll be the exciting conclusion. And as we get to that conclusion, we're going to deploy locally and just kind of see how that goes, and then out. And so by locally here, so there's 2 forms of local. There's local just Docker, and then there's local Kubernetes. And then there's Kubernetes, like cluster that's actually remote kind of thing. So I still have to kind of reword some of these, but conceptually we can test our model locally without deploying it anywhere with just Docker. Then we could use Docker's Kubernetes locally. Then when we're comfortable, we could deploy it to a real Kubernetes cluster that lives off of our machine. And then SageMaker is a managed service for this kind of stuff. SageMaker does not use Kubernetes, just in case some of you were wondering. It's more closely related to their, what's it called, ECS, the Elastic Container Service, which will soon support Kubernetes, but that was announced at the same time SageMaker was announced, but is not generally accessible right now. So we build our own Kubernetes clusters on Amazon using something called KOPS, which is KOPS. And there's instructions here, I think, under cluster, under deploy, or something like that, maybe. Deploy. How to, I think, if you look at AWS GPU, this is how to build a GPU cluster in Amazon. And, there's some tricks here to this particular to this style of doing it. So hopefully once EKS comes out, it'll be a lot easier to spin up these Kubernetes clusters. Okay, so let's get into some code. let's actually go back and follow these steps. So under quick starts, we want to do local. These are actually the same instructions that were there before. We just moved them and made them more clear that this is purely local. So this is what most people start with. Just bumped that up this morning. And this is just to get the model working locally. And so make sure that you have 1.5.18, so it's just updated this morning. If you have any trouble, we have this extensive troubleshooting guide now. We've been taking a lot of feedback from the Slack channel and from our Zendesk support. And you should be able to find your problem here and then deal with it. This is really extreme. If you really can't get Pipeline installed, you can blow away the old version and then reinstall it. Also, we spent the last month getting our proxy support. We found 2 or 3 different ways that proxies were hurting our flow. So in particular, when we build, we are installing, pip packages and conda packages, and there was a couple of chicken before the egg scenarios where proxies have to be passed in. So we have about 3 different ways to specify proxies now, but it's more for second and third line defense. But the main way is to just do it using the CLI, which we'll show here in a second, like how to specify those. Yeah, so just know if you've been having proxy issues, either go to the Slack channel and take a look at what we did, or even just search this repo for HTTP_proxy, and you should see all the markdown that is related to it. Okay, so that should all be working. Okay, so I believe we should have. Let me pull up that window and minimize that. Okay, and pip or pipeline version, I just double check. Clear out my thing here. Okay, so pipeline version 1.518, so we're in good shape. Sometimes this thing gets pinned, especially if you already have it installed. So everything looks good here. We've got train server, which server is basically local. Train cube, this is training on like Kubernetes, training on SageMaker, predicting. So there's training and then predicting. Predict server means just a single instance, and today it's just going to be local. Predict cube can be either our local Kubernetes or it could be just remote Kubernetes. And then we added predict Sage. Also, we've got some work going on with Kafka. So this is how we're able to tap into the stream, the actual prediction stream. I don't have a working version of this on our cluster right now, but if we have time, I can talk through like a little bit how it's supposed to work. But in short, every model that is participating in a particular cluster, or that shares the same like model type and tag. So if you have multiple versions of one model that you're experimenting with, they will all point to a single Kafka topic. And we can actually pull off of that topic and look at the different versions and how they for the same inputs, how they're predicting. And then we're using that to actually populate a dashboard. So it's not just system metrics that like we're maintaining, which is certainly true. That's happening today, but like this is actually comparing predictive performance. Given the same set of my input features, what is actually being predicted, and how far off is my version 2 or version 3 from my control version 1, for example. The other thing is, very soon, we've had this working in the past. It's just making it consistent, but we could actually spin up Jupyter. And what we're seeing more and more people do is spin up huge X1, probably Amazon instances, or, it doesn't have to be the X1s, but, which have 2 and 4 terabytes of RAM, but actually spin up, 500 gig RAM like boxes within EC2 and just have a single Spark, worker and a single Spark driver and, a single Jupyter. And so basically each developer, can sort of own an instance and it's still tied into S3. And, this is kind of a newer way that we're seeing things. This is actually stuff we had done at Netflix years ago where everyone had their own environment. It's very expensive. It gets cheaper as you can use Kubernetes and, you could share physical resources at the container level. So we're kind of staying ahead of that curve a little bit. But so same thing, you can spin up an Airflow or even spin up a separate Kafka cluster for something different than that use case I was describing before, which is the predict Kafka stuff. Okay, so we can do a quick, let me just clear this. If I just do pipeline naively, because I don't know what I'm doing, this is going to show me, you can do pipeline help, which I think basically just does this. Here's a list of what all these things do. The ones we'll be playing with today are train server. We're going to train a model. We're going to predict on that model. This is all locally. Then we're going to do it on a Kubernetes cluster, and actually we'll do it on a local Kubernetes cluster using our new Docker Kubernetes support. And then we'll use SageMaker and actually get these models pushed out to SageMaker and then run the load test there. All right. And let's see. Yeah, so let's do one here real quick. Yeah, here's some blurbs here on. So when you're building, yes, anytime that you see train server build or predict server build, that's actually building the Docker image. And we're giving it a name and a tag. We're also giving Pipeline a hint as to what this model type is. There's ways to detect it, of course, but for right now, we're just asking the user to explicitly tell us if it's a TensorFlow model, then we can start to apply TensorFlow optimizations. We can use TensorFlow serving, things like that. We're also passing in the path for the model, and this is actually physically, so everything here, by the way, starts inside of this. We would git clone. These are sample models. So I've already cloned them. Let me just make sure I have the latest here. So that's this repo. And we clear, and we can do, so we're actually inside this directory already, so we can list it. Let's actually list out the contents of this. So here's our actual model. Here's a, this is, if we do cd TensorFlow census model, boom. So this is a TensorFlow model with the name census, and then every model directory has these three subdirectories. There's the actual model, there's the input, so this is input data, and this actually is broken down into 4 or 5 different types. So I have input data used at my training time, validation. This is that typical 80, 10 percentage split. Okay, and then we have some data that we'll use to predict as well too. Has never been seen. And we've got the output. This is where our model gets when it gets trained. We are exporting it as in this particular case, because we're using TensorFlow, our training code is actually going to export a model in the saved file, saved model format, which is a specific format here. Let's see. Well, actually, this particular one we're not. We're using the old model. But yeah, anyway, so let's just run through this here. So this would be training a model. So this is all done through the CLI, and we've got there's a bit of complexity that's all hidden from you by the CLI. So this is also where you pass in -- HTTP proxy and HTTP proxy S. Once that's done building, sometimes this gets stuck. Let me actually restart Docker. Okay, so I have to wait for Docker. It should take about a minute to fully restart. Then we'll train this model. We will start it. We can actually look at Tensor Board. so directly inside the model. These are all running the latest 150 RC1, by the way, that just came out 2 days ago. So I had just recently updated. I'll be taking a snapshot and labeling probably later today version 1.6. And so, we'll be freezing 1.5 here, and then 1.6 is really going to focus on the Kafka-based, the tapping into the stream, also continuous training. So, not just predicting with the Kafka stream, but also training, feeding data back in. And that's the real power of these like neural networks, is that they can really handle this case where there's incremental data coming in. These neural networks love more data, and if there's no time component to them, it's even better, because just keep passing in data, even old data that was discovered, something like that, right? You can just keep passing more and more data in, and these weights change based on that new data. So that's going to be kind of the killer app that we'll be showcasing for customers and potentially future investors. Okay. All right. So it looks like this did come back up here. Let's do. Okay. There we go. Sending. All right. So that's going to. This should be pretty quick. So what's happening here is we're actually looking at the pipeline conda YAML. That's in the models file. So I'm going to show you. Census model. So this is, at some point there will be tooling to, generate this, and that's the easy part, right? It's getting all this stuff to actually work together. That's the tricky part. So what we're doing here is because we found pretty much everyone is comfortable using Conda, we stuck with this as the main Conda. So instead of using like requirements.txt and Conda YAML and like that kind of thing, we are able to actually do both right with the this Conda YAML. So this Conda YAML actually can support pip install, and that's just another section within the YAML here. And so anything that uses pip, this is actually pipeline. This is all this is all open source stuff here. This is actually under the pip module here within GitHub. But these are libraries that help you connect to Kafka. They have TensorFlow serving support in there, and all kinds of little goodies. Tons of loggers. We're about to add Datadog. That seems to be the #1 request coming from folks is when we log metrics. Right now we're logging to Prometheus, because it's pretty. It's a pretty thriving project. It has really good Kubernetes support. It's kind of built into Kubernetes, and it's very easy to operate. So if you look under this pip, I couldn't really find a better name for it, but pip under pipelines, root, like GitHub org, you'll see the difference. So this runtime is actually just specifying in its requirements txt these other 3 projects. Also, we're using Cloud Pickle. That seems to be the best one. We just had a support case this morning where someone was pickling with 2.7 on the training side, and then was trying to serve it and unpickle it with Python 3, and that doesn't seem to work very well. So, but for the most part, Cloud Pickle's been pretty good. We've had people use Dill and just the straight up one from Python itself. But and so in this bag of tricks here, pipeline-runtime, you actually get loggers, you get some commonly used models like TensorFlow serving, and you get monitors. This is where we're going to stick in Datadog. So right now we have a Prometheus and Rally package. You'll be able to instantiate this with your like Datadog coordinates, and then start pumping your metrics out there. Okay, so all that was slurped in. This model was slurped in, this predict method. Here's an example predict method here. You'll see the logger. in action. You'll see here we're using the commonly, so like this is a very clear example of using all three of these like open source libraries here that we give to you. So there's Prometheus, there's TensorFlow serving, and then here's just our straight up logger. This is where you can easily append a like Kafka logger, which we'll do in probably the next month's call. That's stuff I'm going to be demoing these next couple weeks. So especially up in Seattle next week too. That's a big one. All right, and all that you need to participate in the pipeline framework, like you don't even need any of this stuff actually. You could have a super bare bones version. This is all just to make the metrics show up nice, you know, with good tagging, and so you can differentiate the models when you're running multiple models. But really, all you need is this predict method with bytes going in and bytes going out. This is some new, you know, Python 3.6 type functionality where you can actually specify the return types and the argument types. We're sticking pretty basic and just doing bytes in and bytes out. This lets us use the same underlying logic, but, you know, swap out the input type can, you know, if we're going to deploy the same predict method behind a Kafka stream, we would want to pass in like Avro, you know, but for like this particular version, we're going to be passing in JSON bytes off of an HTTP request. So, you know, kind of a common sort of REST API thing. So like we're essentially creating a REST API from this model. And you notice we have these transformers. Now these are not required. We do encourage these because you can actually set timings. And so here we could actually see how much time is being spent inside of this. So like you could either do the with monitor, which is a Python context manager, or you can even decorate with add. So, you know, showing a couple different ways to do things here, not to be confusing, but just to show that there's different views. There's, you know, different ways to use these things. So previously people were just putting all of this logic into the predict method, and then it was a bit difficult to see where time is being spent. And sometimes, in fact, most times we find that these transformers actually take like more time than they should. It should be that this particular call is what's taking most of the time. This is the actual prediction. This is what's, you know, running through the neural network or calling Scikit-Learn's predict method or like that kind of thing. So, and then also there's the transform response. So we can see how much time is being spent. So this, our particular example goes from JSON to NumPy, passes in NumPy into this predict method. TensorFlow accepts NumPy and can convert it implicitly or explicitly or something into TensorFlow tensors. And then same on the way back. We can actually, we're taking NumPy, which is coming from our response from TensorFlow, and we're converting it back in to JSON. And that's what we're then returning to the user. Okay, so that's an example model that's been burned in here. Oh, so actually this is the, I was describing the prediction side. Up here, we actually built the training side, which picks up this pipeline_train. And this is even easier. As long, so to, you know, to be as generic as possible, all we need is, I think, a main method here. And if there's a main method, we will call it. And that way we started to kind of impose more structure here and, you know, provide opinions. And we just found it, you know, really wasn't worth it. These are more offline type of jobs anyway. And, you know, the more structure we impose, the less, you know, people seemed to be a bit frustrated. So here, one thing to emphasize on this is that we're using the new experiment API and run config and what else here? The estimator API, and following some of these like newer practices from TensorFlow 1.4 and continuing into the latest TensorFlow 1.5. So, okay, just to keep moving here, let's do the, so we've got, we built, now this is what you would actually upload. This, if I do Docker images, I should see this guy at the top. So let me got a lot of images here, but this is the latest one that was built. Now we're building quite a lot of stuff in there. These can certainly be slimmed down. Right now, you know, the sort of dev versions, there's tons of bloat because we have you know, TensorFlow, we have Tensor Board, we have all kinds of stuff built into this single binary. This is what you would actually upload to AWS SageMaker, and it could scale out the training for you. But for the sake of time, let's just do this locally. So I'm going to run. Okay, so we just did the build. That creates that single Docker image, which you can deploy either on your own Kubernetes cluster, which we scale it out and will actually train in parallel in a distributed TensorFlow manner, or SageMaker supports custom Docker images as well, even on the training side. Okay, let me let me just stop the existing one. Okay, clear. Okay. So if you notice also, I'm actually, for debugging purposes, and this has come in really handy, I asked people to, or I'm actually printing out the exact Docker command that we're running to start this. And this helps me debug if there's anything, you know, funky going on. So we are pointed, this is just a local single Docker image, so there really isn't much to it, but so let's take a look at the logs. All right, so we actually see some of the training here. I didn't do it fast enough to actually show it scroll through, but you'll see that's, and then, but I do have it waiting a bit, so if you notice, this is what was output, 15160, blah, blah, blah. So let's see, 38225. So I should see at the very bottom, 38225. So this was just built. I'm on the West Coast today, so about 9:43, about a minute ago. And now, and so I have, yes, even though training is done, I have it set up so that it will wait and sleep about 5 minutes to, you know, give us time to actually look inside of Tensor Board. And that's adjustable and all that kind of stuff. But we could actually, let's see, toggle them all off and look for just the one that we just trained. And we can compare it to one from before. You know, we can look at the graphs. We could see which devices were used, CPUs, GPUs, TPUs, things like that. So it's kind of cool. So now this is all local. There is no cluster involved. Okay. Let me stop that. So that's the training side. Now, this is where I need you guys to stick with me here, because we're going to actually shift over on the predict side to a different model. And that's just because I just haven't had time to connect the two examples. But so bear with me. So let's say that we actually built the MNIST one. We're switching over to MNIST now. Let me clear this out. And we are building. So let's dissect this command a little bit here. We're saying this is the name of my model, MNIST. I'm just giving it some arbitrary tag A. It doesn't matter. It's some version that means something to us. I'm hinting that it's a TensorFlow model. I'm giving it the path. So just like we did with the census model, we can crack open back here. Boom. We have the same thing. We have conda environment YAML. Same version of the runtime, hasn't changed much. And we're up to the latest TensorFlow from 2 days ago. Let's look at, oh, yeah, by the way, here's one way of setting the proxies. You can do it in this pipeline, in this conda RC file. That wasn't working for us because of the chicken and the egg problem, but so now you have to pass it in through the CLI so that Docker can actually burn it in. And let's see, one sec here. So if we look at the predict, same kind of deal. So very similar. We're actually because this code runs within that container and these environment variables are set, we're able to get the name and the type and the tag, the version, all that from the environment. same kind of deal where we're wrapping 3 specific methods, and this comes in handy because you can see where time is being spent separately. So like I mentioned before, let's see what else is in here. We have a one-time setup. This was another attempt. I put this in and taken it out at various times during development. We were trying this out. This is one time at build time. This gets slurped in, but is not being called on the actual prediction path, and that's on purpose. So we've actually had 2 use cases for this. One of them was the proxy. Any build time things that need to get pulled in from pip or from conda have to go through that. But the other use case was on the prediction side. We've had people that needed things like ODBC drivers. They needed upon loading. So this predict method, just in case you're wondering, the life cycle of this, there is a part. So this initialize method gets called once, and this is just one time, upon startup. And we had people that were loading in reference data from a database, right? So they would be pulling in, state codes or so things that would get joined into the prediction. We try to minimize that as much as possible and have them do it on, the application layer and keep it out of here because it could potentially slow things down if used improperly. Okay, someone's asking a question here. Okay. Can you post in a question into the chat there, and I can get to it in a sec. Starting to run out of time here, but so where did my chat thing go? Oh, there it is. Okay. Yeah, just post it into the chat, your question. Make sure you select not all panelists, but all panelists and the attendees. Okay, I'm going to continue with the story here. So we've now built a Docker image that is capable of serving your model. And here we're using REST. And so let's go actually start it up. So again, this is all local. This is the physical Docker command that's being generated to start this model. This thing started up. This is giving you a hint as to where the ports are. You can actually override these ports if you do want to run multiple models on your local machine. I had a couple of people ask for that, so we do support that. But yeah, and this gives you instructions on how to actually override those. Okay, what's cool is we can actually tap into the server logs and make sure everything's starting up properly. Like our routing layer, our web server, everything, our model server is starting up good. This is likely what I would ask you to send me if there is any support issues, because I can tell right away what's going on. You can most likely tell on your own as well too, but certainly shoot me the logs and I'll help you through it. We've got a way then, so again, we're in this models directory. This models directory has the model that we're actually serving is MNIST, and I mentioned there's a couple subdirectories there, input, model, output. You can just ignore these Python notebooks for right now. This is another effort that we're doing in parallel. But if we crack open the model file, or that model subdirectory, we see that. Now let's crack open the input. So input, we have this predict, and this is just some JSON. This is a sample JSON, and that's the one that we're going to use. I think this is a old dangling JSON file, but this is the one that we're going to use, which is a JSON representation of a number of a handwritten digit. Okay, so fortunately, I have all these copied and pasted or in here, so we can just copy and paste them. Let me clear. So let's dissect this. What's going on here? Oh no, did I screw that up? One sec. There we go. Okay, so I have to change the call there. But so yeah, let's dissect this. So we're saying predict server test. We're giving it a model endpoint, which is localhost. This way, you could use this exact same thing when you're calling SageMaker, except you would which we'll do here in a second because I have the SageMaker stuff running. And what else? We're passing in the actual path of that request, of that JSON file. So let's go down to, oh, and then you can, let's copy in this one and we could do like a mini load test. So again, this is locally. We're going to do 1,000 or like 100. Let's see, I did the wrong endpoint URL again. I forgot I changed that, made it easier. Okay, 1,000, boom, boom, boom. All right. And you can even do a curl. Yeah, I know everyone likes to do the curl thing, so this will likely require this to be removed as well. Boom. There we go. So this is like an image being passed in, and the output is the highest value here will represent the actual letter. So this would be, so there's 10 values that come back within this array, and the highest value is take that index, and that's the digit. So 0, 1, 2. So it looks like this number is a 2 because that's the highest, most confident value. Okay, and it kind of thinks it's a 3, 4, maybe a 5, because this one's higher, but this is still the highest. Okay, so you can have fun playing with that. Here's a quick way locally to look at, let's see, strict dashboard. Oh, all right, I have to fix that. I was playing with the web server the other day and okay. Okay, so yeah, this would basically show you, yeah, I'll fix this right after. It's going to show you these metrics. So let's stop it. Also, there was a request recently to have an example using Scikit-Learn, so I just tacked it on for right now to this. It's all those exact same commands, except it's going to be linear, regression, type scikit, and literally what this will pick up will be this scikit subdirectory and the model that's in here. So it'll package that up. This actually pickles. This is a pickled scikit-learn model. This predict method has one single initializer that's called once that unpickles, and that's this initialize method here. It's going to unpickle it, and from that point on, it's going to use this as the underscore model throughout the rest of the. So here's the actual predict method here. Okay, and then yeah, here's a case actually where we use a context manager for the timings on this predict method, but then we use a decorator to create the timings for the transform request and the transform response. And then you would make the same call with the endpoints there. All right, let's get to the SageMaker stuff. We have a couple minutes left. Let's see, there's a quick start for it. And I've already prepped it because one thing about SageMaker, when you actually load or push your models to it, it takes forever to start. It literally takes 15 minutes because it has to pull down the Docker image from wherever. You can upload it directly to the Elastic Container Registry itself, or you can have SageMaker pull from your repo. And I'm having a pull from the Pipeline public repo. But yeah, either way, it's pretty darn slow. Okay, so we've got this version installed already. We've already got the models. I've already done this, so just to tie it back to kind of what we're doing here, we're using the exact same model. So let me just walk you through here what this looks like. So stepping through this, it would be predict server build, the exact same thing that we did before, MNIST. I'm just giving it a slightly different tag. The other tag was A. This is CPU. It's of type TensorFlow. It's pretty much the exact same model. I have it separated here just for clarity. And then you don't need to pass this in, but we are going to pass in, because by default, it will do CPU, but you can also do, if you flip over and make this GPU, we will actually pull in the PipelineAI TensorFlow serving. It's a custom build of TensorFlow serving that has all of the GPU optimizations and all the Intel optimizations. But this is actually one of the harder things to do with TensorFlow serving, is to get the GPU. So the goal for this experiment is to compare CPU to GPU on the exact same Amazon instance type. So it's actually two separate instances. But, and so I think if I pull up SageMaker, this will probably make a little bit more sense. So yeah, let's assume that we built this and built the GPU version, which is next. I had done this right before the session started, because it does take about 15 minutes to get everything registered. And we're pushing this image. If you don't specify anything, it's going to try to push it to Pipeline's repo. So just know that if you push it to your own repo, which is fully supported, that all you have to do is pass in a couple extra parameters. This is where you can give it your ECR, the Elastic Container Registry coordinates, and it'll upload it there. And I've already called this. So this is the part that takes like 15 minutes. This predicts stage start. So similar to how we did predict server start, which is just, local single server. Now we're telling it this is the CPU version. You have to give it like this like goofy AWS IAM resource name, and then you can give it an AWS instance type. And I think I have the list of instance types. So yeah, here's an example of the goofy ARN thing for the IAM role. And the one slightly weird thing about these instance types is that they have a prefix of ML. So this is actually the P2 X large. I have access to the regular P3s, right, like the X larges, but which are the new Voltas. The problem is this ML thing, I didn't realize this actually comes from a separate pool. And so just last night I had requested access for, and still hasn't come through yet. But so like, just keep in mind that there seems to be this difference between regular, P2s and P3s and ML.P2, P3, things like that. Okay, so if you'll notice, I'm actually using a GPU instance to deploy the CPU, and that's on purpose, right? Like the CPU version of the model, that's intentional. And then also I have a GPU version also deployed on a separate instance, but of the same type. And so this is so that there's no, tricks up my sleeve. It's the same instance type. It's just one of the models will be using GPU, and then one of them won't. And let's see. So I think I already routed. So this is a way to route traffic between, let's see, the CPU version and the GPU version. And I'm saying 50% and 50%. So yeah, 50% goes to one, and then 50% goes to the other. So I have done all that, actually. I go here. If we go history, you should see it. Yeah, so that, like, those were the last like 3 commands that I ran here, was to start the one model, start the next model, create a 50-50 split. And now, and so if we go into the SageMaker UI, it'll look something like this, right? 50%, 50% behind a single endpoint, which is just predict-mnist. Okay. And let's get to the good stuff. Let's actually load it up. Predict-mnist. All right, let me go into the SageMaker UI. Okay, so there's the 2 models that were, okay, endpoint configuration. Looks good, 50%, 50%, endpoint, predict-mnist, not pass the ping health check. Oh, okay. All right, so something happened here. And we'll have to rebuild that. But essentially, I always make a million changes right before these calls. All right. So back to here, we will see, so this is what things will look like. The CPU will be returning, and we could see the actual variance. This was the CPU version. We know exactly this is the GPU version. What's really cool is that you can click endpoints, and the SageMaker guys actually have links directly to the metrics for either the instance system metrics or for the actual prediction latency, prediction throughput. And you'll see that pretty much, this was a pretty quick example, but that's the CPU version. Higher is bad because this is latency, and the GPU version was consistently quicker. And so, keep in mind, there's some other knobs that we've turned on by default, like the request batch size, and these are things that we are exposing through Jupyter Notebook for data scientists to experiment with. So this wouldn't just be, for example, the CPU version or the GPU version. This could be GPU version with 1,000 as like the request batch size. So that means every 1,000 records that are passed in for prediction will get batched up into 1,000 and then all like predicted together, and then compare that to the MNIST GPU 500 or something like that. So these are some of the knobs that we're exposing. Okay, so yeah, and this is because people always ask on Stack Overflow, how do I know if TensorFlow Serving is actually using my GPU? This is how you can tell. If you haven't built TensorFlow Serving from source, and you will definitely not be using the GPU. This is the version built from, or that's just default. If you just pip install it or apt-get install it, this is the version that we've built from source that has access. The cool thing about this is that SageMaker, the AMI that we're using, is the standard deep learning AMI, which supports Ubuntu 16.04, CUDA 7, CUDA 9, CUDNN 7, all of the things that the latest TensorFlow 1.5 supports. So we've got all versions up to the very latest as of TensorFlow 1.5, and so that actually takes quite a bit of work. If you do want to see some of these Docker images, actually, I should probably add these to, let me pin these. So this would be TensorFlow. Let's see, how do I pin? TensorFlow Serving and TensorFlow. Let me get rid of the pip thing here and do TensorFlow. All right, so these are actual forks, from the TensorFlow projects, but with a custom Docker file. And I can make that more clear where it is. But for example, so let me go to the TensorFlow Serving one. And these were updated as of this morning, like about 2 a.m. this morning. Docker. So we could, do like a diff and see how this differs, if you're really curious. But we've added Conda in here. We've made sure everything's on CUDA 9. We are using the latest Bazel, which is the goofy build system that TensorFlow uses. We're also, pinning to a particular version of TensorFlow Serving that we know works. And then also we're making sure that we're using 1.5 branch and let's see what else. Also, these compute capabilities, these are really important. If you're using P100 or the K80 or the V100, that's going to determine which compute capability. I think I've got all of the ones that work across both Amazon and Google. 5.2, 5.3 is the G instances. I believe 6.1 is the 6.0 or 6.1 is the Google's P100s, and 7.0 is the V100s that are offered by probably Amazon right now. We're doing everything Python 3.6. For the most part, the default builds that come out of like TensorFlow are 2.7. Python, it's sometimes a little tricky to get 3.5 working, that kind of thing. Okay, so let me do one more thing. There's still a bunch of people on, so that's good, even though I've gone over. We are recording this, so we'll get it out there, but I do want to show an example of, back to quick starts, Docker Kubernetes. So as I was showing earlier, we can get Kubernetes going, make sure that you have this, at least this version. The first version to ship is Kubernetes 1.8.2, which is good. It's not 1.8.6, which is, I think, the latest. There's even 1.9 now, but for the most part, we're running on 1.8.6, so in the 1.8 series. One thing that you need to do is, let me clear this out. So they have this kind of default, when you install it, it's called Docker for Desktop. That's the name of the context. And if I kubectl get pod, there's nothing running. I have another like Kubernetes instance or cluster here, AWS GPU. There's a bunch of stuff running. This is where the community edition runs. Here's some sample models. Here's that streaming stuff that we're playing with. Here's some of the dashboards. But I'm going to go back to the empty and local, Docker for Desktop. This, to me, would actually probably be like Kubernetes for desktop. They purposely call it desktop instead of Mac or Windows because they will support both. Okay, so we already have the CLI installed. Because we're going to be doing some advanced stuff, like later on, you probably want to install Istio. I already have this installed. So I've pretty much done all of this. Did I do this yet? And then I got to do this one. This should be quick. So keep in mind too, this is one thing I spend a lot of time talking to our users and customers about is the burning in all these assets at build time is so important. If you rely on dependencies to be loaded when you're trying to deploy, we saw this with Netflix. That was one of the outages of, Christmas 2013 or something like that, was that there were like dependencies. So we were trying to auto scale and all of a sudden we lost S3 or there was a network partition like within Amazon that we weren't expecting. And had we burned everything in at build time and not relied on anything when we're starting to auto scale up, this would not have been an issue. That's the immutable deployment architecture, right? And that's pretty much always how you want to roll. It's not very natural way of people's thinking. So, it seems a bit awkward and, why are we doing this? I just want to point to S3 and, slurp in my model at build time. And then I always explain the downsides. Really get your models built. Either you can put this pipeline CLI behind your like Jenkins. You could also upgrade to the pipeline, standalone, or like the enterprise edition, which has all that for you behind a REST API. You just, ping it, give it your S3 bucket, and then, we start what's basically a Jenkins job, and then goes through all the those motions to output this executable Docker image. Okay, and so once these are built, we will actually, so we're calling predict kube start, which is what we used to use on my remote Kubernetes instance, which is running the community edition and all that kind of stuff. Here we're actually pointing, because of the context, we're pointing at the local Kubernetes cluster. And we'll do the same thing where we will route the traffic, 50% to model A, 50% to model B. Now A is, so this is two different learning rates. So, and I think we end up getting the same results just because this isn't a lot of data and because of the precision and things like that. But while this is going to, I should point out that when we speak again next month, we're going to be talking about the streaming, about the incremental training off of the stream, and truly continuous, like training of our models and then deploying of these models with the newer weights. And but that also will be discussing, let's see, so there's one more runtime. So before, for the SageMaker stuff, I was showing that we have GPU, we have CPU. There's going to be a third, and it likely will either be TPU but it's most likely going to be the new Tensor RT. So this is a project out of the NVIDIA folks. I just had happy hour with them on Friday, where you run your TensorFlow model through a post-training optimization step. So you've trained your model. We now point your model or run a tool that the NVIDIA folks provide on your model, which fuses together layers, does all kinds of weight quantization, and gives you all these different sort of optimization techniques. And then it will generate essentially its own sort of bytecode or intermediate representation, which then gets picked up by the Tensor RT runtime. So if you remember, we were passing in, here we pass in that the model type is TensorFlow. When we next talk, there's going to be model runtime equals Tensor RT. So this is saying, yes, this is a TensorFlow model. Do your TensorFlow thing, but also run that same model through this deployment optimization or this runtime optimization step provided by Tensor RT. And then instead of putting it behind just a regular TensorFlow serving runtime, it's actually going to package it up into this Tensor RT runtime, which can also handle web requests and HTTP requests, and can also run behind a Kafka stream and that kind of thing. But so what we'll do for this next time is compare TensorFlow serving CPU, TensorFlow serving GPU, and Tensor RT GPU, all using the exact same instance type. So it's all apples to apples, and they're claiming 7 millisecond latencies. I think what were we seeing here? 20-second latencies on that one diagram here. Okay, so looks like A finished. We're going to wrap up here in a bit. Let's just so let's call the next. So here we're just calling start, and let's do kube get pod. Okay, so that's initializing. Now let's call kube start. So this is saying take that model that you just built and get it going. Now we're doing some advanced things beneath the covers to help out with routing, and some other things, so we could actually steer traffic similar to what we're doing in SageMaker. Hope these things come down okay. All right, so these are likely, if I do describe pod, they're likely pulling. Right, yeah, it's pulling these things down. And actually, yeah, I think we're supposed to push them up to the registry also, just to be safe, but I think it'll pull ours from local. Yes, anyway, so fast forwarding here, we would do kube test. We would, which is the same as the Sage test or the server test, which is local. We give it some JSON data. We give it 1,000 concurrent users, and we would see what's very similar to what was coming out of SageMaker, which is here's the variance. the CPU. Here's the GPU. Oh, yeah, this was CPU, but with the 0. So yeah, this is A, right? Yeah, the A, which was 0.025, and then MNIST-B, which was 0.05. And these actually, I think, come in pretty similar, maybe slightly different here, 315, 136 kind of thing. But and that's just because we changed something on the training side, right? So we used a different learning rate. And one really cool thing is that we could actually scale with just one single command, right? So again, you know, this will be all behind a nice UI. It's still pretty command line right now, but saving the fun stuff for last. I'm going to switch over to the other server, see AWS GPU. This is the pod. See how many pods we have here. So we have a single MNIST-A. I could actually do, let me run this one command and say scale out MNIST-A, give me 2 replicas, and scale out B and give me 4. So now we have, let's see, this should level off. It only have 2 running at once of these, and then 4 running of these. So it's already starting to like terminate. Yeah, typically, you know, it's gonna kill the old ones and then spin up new ones, but like try to do it in a balanced manner. And then we would run this again, and yeah, we could see the split of traffic, you know, part of it. So like back here, 50% was going to Model A, 50% was going to Model B, and that was because of this route rule that we specified up here. Okay, so I think that's it. Got a couple bugs to fix, as always. You could tear all this stuff down with, you know, just a couple commands if you're worried about messing up your you know, like test, like Kubernetes environment, whatever. You can certainly tear things down easily. So I believe that's it. Let me check for questions. Okay, no questions. Yeah, whoever had raised their hand before, just shoot me an email. And I'll post this here in a bit. And look forward to next month. Talk to you soon.